presentation talked two very important concepts. One is resource assessment. The other is resource classification. I think there are some different. The assessment is not classification, but they have very close relationship. So my question is, what's the difference and the relationship between resource assessment and resource classification? This is very important for the authority to create the standards for reporting the resources. So we should make clear the difference between these two concepts. We don't want to have too much technical issue. The assessment, I think, is involved in more technical issue. The classification, I think, is involved in more standard issue. So I think that we don't want to include too many technical issues into the classification system. That's my question.
I'm just going to start and ask Pat. Classification would mean actually putting samples into a particular box according to the rules that have been set for determining whether something is a resource or a reserve, whether it's been measured or indicated, proved, or probable. Assessment is a more general term, but before I leave that as the final word, you work in this field.
Thanks, Caitlin. I had a feeling this was coming. Yes, Caitlin's summary is quite right. Resource assessment, which I guess we'd call resource estimation, is the process through which you interpret the data you've collected and the geological framework to come up with an estimate of, in this case, obviously, abundance in land-based deposits, usually the tonnage, and the grade or the quality of the estimate. That's through the sampling that you've done, however that's done. And seabed nodules obviously have certain issues to do with sampling, including how you estimate the abundance. So the estimation is really managing the interpretation of all that information to come up with the best estimate you can of the quantity and quality of the particular mineral. The classification relates really to the confidence that you have in that estimation. Because as you can imagine, you start with very little information and you move through the process of more exploration into more and more information. So you start off usually at the lower categories of resources, such as inferred. As you get more and more information, you improve the confidence in your estimate of quantity and quality. You can then progress to the indicated category and eventually to the measured category. So I think that's probably a summary of the point in the question you were asking.
I think that's a really great question. Absolutely really gets to the crux of the. I can talk for about a half an hour usually on answering this question. I'll try and limit to this because I actually written some notes about similar issues. I think this is making a lot of whack. I think a key thing that we need to keep in mind is that every assessor of volumes is going to come up with their own unique evaluation of what the quantities are associated with that. We need to be very careful that we recognize that resources, when they're assessed and then categorized, will vary by assessors. Two different individuals looking at the same prospect will come up with different numbers. And there's a lot of reasons for that. There's the skill involved in the assessors in doing this, but there's also the experience that those assessors have. All geological deposits are an analog for other ones. So if I'm someone who has a lot of experience in one basin working in one type of geology, I'm going to have a more confident ability to make an assessment of those volumes. The other key issue is that each individual looking at the modifying factors and how they can apply to making those assessments will also come up with a different value. And this can depend on which stakeholder group is making the assessment. So an individual who's working in a business, someone in industry making an assessment of a project has to have different risk factors on those modifying factors than someone working for the state government or whatever national government has jurisdiction, or whatever the government has jurisdiction over those values, because they have different views on the legal and environmental issues that would be associated with the development of that project. So a simple example of that would be an industry working on a prospect where they have a right to develop a project may be limited by a certain time frame. They have a license in which they have to extract the volume by a certain date. A government that owns that license, that owns the right to grant that license, isn't limited by that license amount. They will make an estimate for the ultimate extraction of that project in a full field life. That's just a simple example of where there can be confusion in estimates when they're viewed from different points of view by different stakeholder groups. A business can only view what they're going to be developing within their entitlement period, whereas the government would want to look at a full life exploitation of the deposit. A really good example of the difference in estimation on the assessment side that I can give you is from the petroleum industry is in 2004, I'm sure many of you remember, there were a lot of press about the U.S. SEC coming to grips with enforcing its classification system for oil and gas reserves much more strictly. A number of companies had significant reserves downgrades in 2004 and 2005 as a result of that. There was one field that was just having its initial booking of reserves in the Norwegian North Sea called Ormen Lange. And this was an interesting field because the ownership of it was almost every big company. BP had a portion of it, Shell had a portion of it, Total, Norsk Hydro, Statoil. There were a lot of companies involved in this field. And every one of those companies had a completely different assessment of the value of it that got published in their annual report. And the range was a factor of 3 for proved reserves. Factor of 3 proved reserves. Each of the companies was called into the SEC to defend their numbers, and each of them defended their numbers successfully. So at the end of that year, I'm not sure what the value was to the investor to see such a large range in numbers for those values, unless they were able to look at the individual companies and see, well, this company has more experience in that sort of environment and can have a more certainty about the volume that it's ultimately going to recover from it. So even with really clear assessment rules and classification rules, there could still be very big differences in the numbers, and we need to keep that in mind.
Thank you. And as we move on now to perhaps more comments or questions in regard to Caitlin's presentation, which obviously was quite wide-ranging. Yes, please.
Thank you. I think it was an excellent presentation on the elements that need to be reported in case of resource. My limited point is that whenever we talk of deep seabed, particularly for nodules, the focus on extractive metallurgy for metal extraction doesn't get the kind of attention that it deserves. Particularly, let's say in case of land deposits. In the case of land deposits, perhaps it's not as relevant because you can sell the product, mineral as a product. But in this case, the nodules, I don't think there could be buyers for the nodules. Therefore, the end product has to be metal. And just because you mine nodules, well, that's not enough. You have to look beyond the ocean and what do you do for metal extraction, and what is the infrastructure available and to be created there, and what kind of product mix that you are planning to generate to make the total integrated project viable. Without extractive process becoming viable, the nodule mining can never be a viable process. So, I mean, I could expand on this, but I think this is my limited point. Thank you.
I agree wholeheartedly. When we were doing our scoping study back in the late 70s, we chose to do an integrated project because there was no intermediate market for nodules. There may be at some time when we have processes that can deal with different compositions from different regions, when there's enough there to assure somebody that they can make a processing-only system and set a commercial price for the nodule. But for now, the evaluation has to look at the processing, and in fact, the selection of a different process will reflect what you think you're going to market. The choice between a hydrometallurgical or a pyrometallurgical process will be an important one and will be determined in part by what metals you want to process. Or a combination one if you're using the pyrometallurgical to get a manganese product and hydrometallurgical to get other products. So all of that comes down into the economic assessment. And in fact, since generally the economic assessments I've seen have shown half of the capital cost at least to be in the processing side, yes, you have to evaluate for the whole system between the seabed and the marketplace where your income's coming from. You can't set an arbitrary number in between, for now.
Thank you. Back, please.
Touched on, which is that of the role of the competent person. So for my sins in a previous job, I was actually coordinating a number of these guys for a rather large mining company. And the group I worked for had a very diverse range of deposits. And mineral resources and ore reserves can be pretty much as complicated as you'd like to make them. And the competent person in this business is really your guide. They're the person that you will rely on in the end to give you the security that you need or the confidence that you need in the outcome. Because things do change. Hopefully your resource doesn't change, but I've been in situations where that has happened. And when your resource changes, it's a bit like the earth moving underneath your feet. And you can have all the reports and numbers in the world, but you will turn to your competent person and look them in the eye and try and find confidence that you can believe, say, in your new set of numbers that are coming out, because your investors will certainly be looking at you at the same time. And then with reserves, because the metals market is so dynamic, your reserve competent persons will always be under pressure to, if not foresee the future, have plans in place to at least adapt as things change. So I think in putting forward a lot of regulations and a lot of expectations, which is what we need to have for such a valuable mineral resource, it's always good to bear in mind that we don't need to be across all of the complexity right now. We'll either get or we'll develop competent persons who will manage a lot of that and adapt with a lot of that as time goes on. Thanks.
I'd just like to say that I hope that you bring that up in the discussions on the competent person again, and think in terms of, is there a role for the Seabed Authority in fostering that education and interchange among people who are or wish to be competent in seabed minerals? How can we help, or can professional societies provide that? Or can business provide that as a professional training course? So all of those things that would help and make it available to all people.
Any others from the floor? I know my co-chair has a question or a comment he'd wish to make. If there's nobody got their hand up, I'll pass the microphone to Mike.
Thank you very much, Caitlin. I was pleased. This was the first presentation, first day, and I'd like to ask you about your first slide. which was you started with stakeholders. And I think if I could summarize your presentation, you showed that there is this evolution from accounting standards going forward into resource management more broadly. And you had stakeholders, you had government and organizations, mineral developers, investors, and securities regulators. If you could look forward, I would argue that one of your forces of change, which was not on your slide, was society. And this goes to the resource assessment question, and I think the point that David was also making. Who are the end users of this information in the stakeholder pool? And therefore, what does the introduction of society in a lot of the decision-making process mean with respect to the classification system?
I actually thought of pulling a social aspect out, but in the near term at least, that's being incorporated into the regulatory process, where sometimes a social license to operate brings in to the evaluation process, or into the regulatory process. What is it going to take to get a resource developed into market? And that becomes one aspect of it. The other, for the Seabed Authority, is the Seabed Authority, I think, has three main objectives: develop the resources of the area, protect the marine environment, and share the benefits, particularly to developing states, but to share the benefits because the industrialized world gets the benefit of a more diverse and stable marketplace. Developing countries get access to technological experience and education, to training, to a range of benefits, and to experiences that may help them in their own domestic development. We could pull that out as a separate part of an evaluation, the social benefits of the society stakeholder in that. And it might be a good idea to do that, but it is a core principle within the Seabed Authority. And becomes part of the resource management. The resource has to be managed with society as one of the stakeholders. So I didn't break it out here, but it is inherent in at least the Seabed Authority's stake in mineral development. Did I sidestep that one close enough?
Thank you, Caitlin. I see the clock ticking on, but there is time for one or two more comments. We are a little ahead of schedule. All right, trying to wrap up. Come on, folks, it is getting close to lunch, I know, but you've got to run around the block 3 times before you're allowed to have lunch. So, well, if there are no more questions or comments, and Caitlin, thank you for what was
And thanks to everyone else for
an important
answering my call.
task to provide the scene setup for a meeting such as this. But if I might make a closing comment and put on my chair's hat for the Legal and Technical Commission, I would suggest that Caitlin's presentation has opened up a whole swath of issues, each of which we could probably spend most of the week, certainly a day, talking about. But I just wanted to draw the attention of the group to the fact that the Commission has 2 immediately related but separate and urgent issues on its agenda. One of which has already been mentioned, and that is the current pioneer investors, by and large, come to an end of their 15 years of contract time in the early part of 2016. The regulations require that any applications for extension of contract must be before the authority, Legal and Technical Commission, by September, 6 months, September of 2015. The procedure and requirements for applications for extension are not yet on paper, but they must go before Council, as the SG has said, no later than July of next year. So the Legal and Technical Commission has until then to come up with that language. That's one task that is immediate and must be done, otherwise the legal implications at the end of the contract start to perhaps become a little complex, and the SG has mentioned that the standard clauses in the contract will start to kick in as to whether in fact the contract is coming to an end, if so, what the contractor must do, or is the contractor applying for an extension of up to 5 years, in which case what must the contractor have in their application for an extension. A lot of what you've said links to that issue. But the second point, which is urgent and before the Commission, which I'd like everybody to be aware of, is of course the drafting of the exploitation regulations, which takes you from, whether you want to talk resources and reserves, to the financial implications. What's it worth? Where you do the valuation, which was, I think, the point that you were trying to raise, that there's no point trying to sell a truckload of nodules or a boatload of nodules. It's the metal that really matters, and that's where the exploitation regulations have a key role to play. So on behalf of the Commissioners, I would ask that as we move through the week, you bear in mind those two tasks that we have, because we would surely like to take away the output from this meeting to guide us separately and yet together on both of those issues that we have to come up with some answers for. The first one, at least, by no later than July next year. We may have a little longer, for sure, on the issue of the exploitation regulations. But once again, Caitlin, thank you for the scene setter. I think he's covered a whole swath of issues, and I'll break now for lunch. Unless, Sandro, you have so, colleagues, I think the meeting is adjourned now for lunch, and after lunch, my co-chair, Mike Stanley, will introduce the next presenter. Thank you.
Ladies and gentlemen, so we will continue with the first item, mining technology for the classification of polymetallic nodule resources in the area, and I will leave the chair to call the next speaker.
Had a very good lunch, and thank you to our hosts for that meal. Our next speaker probably comes to the meeting with the longest tenure in this topic. It's Ted Brockett, and Ted started in 1972 with OMI, and has over the years been involved in 4 different ventures. And if my math is correct, that's 42 years of experience in deep sea mining, Ted, so perhaps you'd like to come up and share some of that experience with us. In the interest of time, maybe you can speak for about 15 to 20 minutes, and that will leave enough time for questions.
Thank you. First, thank you very much to our hosts and to the ISA, and a special thanks to my friend Nee for this invitation. I am very excited and honored to be here. And my talk today is going to be about the OMI Collector Development Program. And I'm going to have to go through these slides very quickly in order to get through it in the 15 or 20 minutes. So slow me down if I need to. In the way of background, Ocean Management Inc., or OMI, was a consortium with 4 primary partners. Inco US Inc., which was a subsidiary of the Canadian International Nickel Mining Company. AMR, which was a German consortium. Damco, a Japanese consortium, and SEDCO, Southeastern Drilling Company, a Texas-based service provider. In 1978, OMI completed a very successful pilot mining test. We were in the CCZ area in about 5,400 meters of water. During that time, we put over 600 tons of nodules on the deck of the mining ship. It was the culmination of a 4-year program, and basically it proved, at least in our minds, the technical feasibility of mining the ocean floor. I don't think I need to show many photographs about the resource itself. You've all seen ones like this. You may not have seen one like this. Some of you have, and I doubt that other than maybe 1 or 2 people have seen this particular image before. But in 1977, OMI conducted a test of a high-speed exploration system. This was a 30 kilohertz based side scan sonar, basically a backscatter system. And the imagery that came out of these tests truly changed the thinking, at least amongst the people within our consortium, about the abundance or the distribution of nodules on the seafloor. So we surveyed about 165 square kilometers during this cruise. The image that you see here is a backscatter image that represents the surface deposit, the nodules on the surface. There were many within our group that did not believe this very mottled appearance was truly representative of nodules. But this particular slide proved that to be the fact. It's probably very difficult to see, but if you look carefully on the left-hand side of the image, if I can find it, someplace about here, there's a very light line that goes down to the bottom. The right-hand image is exactly the same, except that light line has been darkened so that you can see it. In 1976, we conducted a collector test, a deep sea collector test in this area. And that very light line that shows up on the left was in fact the collector track from one of the tracks or one of the passes that was made in 1976. OMI took a team approach to collector development. In fact, they took a team approach to the whole ocean mining project. The project, the PMT was divided into tasks, and each of the partners was given responsibility for certain tasks, and then the other partners were generally given, or one or more of the other partners was given an assistance role. INCO, the company I worked for, had responsibility for collector development, and therefore we did the program management. Internally to INCO, we developed hydraulic and passive collector design concepts. We designed and built a land-based collector test facility where fully assembled test collectors could be tested. And then, of course, we wrote test programs, test plans, and conducted the at-sea tests. Our Japanese partner, they also participated by developing a hydraulic collector design, and they participated in both the land and at-sea tests. Our German partners did the same thing, except their focus was mechanical collectors as opposed to hydraulic designs. I want to mention two key parameters that had a big impact on the way we developed collectors. First is we considered nodules to be a surface deposit only. In other words, we gave no consideration at all to nodules that may have been buried or were otherwise below the seafloor. Second, we took or planned to take a Monte Carlo approach to actually mining the mine site. And what that meant was we would not be mowing the lawn with adjacent successive mining tracts or collector tracts. It was more or less a random course selection. So if you envision a mine site as a large diameter circle, start anywhere in the circle, for example, the middle, randomly select a compass heading, charge off in that direction, mining until you reach the boundary. When you get to the boundary, you spin the roulette wheel. That tells you the next direction to go in, and you turn around and go off in that direction till you reach the boundary, and then you do it again. Well, that had a significant impact on the collector designs in that we did not have any type of active steerage control on our collectors, and none of our collectors were self-propelled. All of the collectors developed throughout the OMI program were passively towed collectors. We followed probably the typical phased development project or program. We started with conceptual designs. We then did laboratory size or base testing of the key or critical components that have been identified. We then did the detailed design, fabrication, and assembly of the test collectors. We did some land-based testing, back to the design phase for the in situ collector test collectors. And we then, of course, tested those collectors. Then it was the pilot mining test design, followed by the mining test itself. One of the interesting factors is that those first three items were conducted simultaneously by 3 different organizations in 3 countries and coordinated by us at INCO. So this is probably an example of the smallest laboratory test that we did. But in the testing, we did or tested for such things as nodule settling velocity, jet sheet nozzle flow, the movement of nodules up inclined ramps and ducts, horizontal nodule transport, entrainment ratios, and hydrodynamic model testing or towing stability tests. INCO constructed what I would call a temporary collector test facility. It was about 200 feet long, 12 feet wide at the bottom, and 12 feet deep. This was a very cost-effective facility that allowed us to test fully assembled collectors. It was very inexpensively constructed, literally by digging a trench with a bulldozer in a local gravel pit, spraying the walls of that trench with concrete. We had developed a simulated, or a formula for simulated sediment, which we used to fill the bottom of our tow tank. And we had also developed a formula for simulated nodules that we spread out in the bottom of the tank. And occasionally, as you see this stripe right down the center, we actually threw some real nodules in there just for comparison purposes. So in this test tank, we tested 2 passive collectors, a device we call a rhombic rake, and the second one was a passive inverted plow. We tested a number of active collectors, including the electrohydraulic, an active inverted plow, the one that we simply called the Domco collector, which was a hydraulic design, and then 3 collectors developed by our German partners, all of them mechanical, 2 of them cutter drum style machines, and then 1 of them the cutter blade scraper. In these land-based tests, we right away eliminated the passive devices as just not being appropriate for consideration in the next phases, and we also eliminated the CDZ design. We followed the land-based tests with in situ deep sea tests of the collectors. The testing was done aboard the German research ship Valdivia. Again, it was within the CCZ area. All of our collectors were tested on the end of a tow cable. We didn't have a riser, and therefore the collectors, they collected the nodules, they counted the nodules, and they put them right back down on the seafloor again. During the deep sea tests, we tested the EH and the active inverted plow designs, the Domco design, the cutter blade scraper. The CDM collector was on board, but it never was tested. Both the Domco design and the EH design, again, both hydraulic collectors, showed a lot of promise. The Domco design actually had some beneficial features that the EH design didn't have, and therefore we chose the Domco design as our primary pilot mining test collector concept. And then we also took out on our pilot mining test the cutter blade scraper design. So in 1978, we conducted the pilot mining test. This was aboard the Sedco 445. We tested submersible pumps and airlift lift systems. Again, same story within the CZZ, 5,400 meters of water. We used 9 5/8 drill pipe. At the end of that rigid riser, we had some cast lead dead weights. We had a dump valve, a vacuum relief valve. Depending on which collector was being tested or which lift system was being tested, we had either 8-inch or 6-inch interface hose. And then on the very end of the hose, we had one of the 3 collectors that we took out to sea. So this is a picture of the Sedco 445. It was a standard drill ship. The one major modification that we made is we eliminated the fixed derrick and replaced it with a gimbaled rig floor and mast assembly. Again, we tested submersible pumps and an airlift system. We had 1,000 horsepower German-made KSV submersible pumps. They were contained in caissons, and these caissons were installed inline in the riser system. We used 2 of these pumps inline when we were testing the 2-meter collector or the 2M collector, and we expected 40 metric tons an hour using that machine and that lift system. We would then put 3 pumps in line if we were using the larger 3M or 3-meter collector, and anticipated up to 60 metric tons per hour. When we tested the airlift system, we injected air at about 2,000 meters. We had 3,000 PSI compressors on the deck, and we were going to test the airlift air injection system using either the smaller hydraulic or the cutter blade scraper design. Our riser was rigid pipe, about 5,350 meters in length. The upper section was thick wall or heavy weight pipe. The middle section, only about 450 meters long, was medium weight. And then the majority of the length of the riser was lightweight or thin wall pipe, and that was about 3,960 meters long. We had high strength rotary tool joints on the end of each joint of pipe. The dead weights were 8,100 kilograms. We could put up to 6 of them on the end of the riser. And the only purpose of the dead weight was to keep the riser straight during towing operations as a means of trying to minimize the bending stresses in the riser. We had a dump valve at the bottom, and again, the purpose of the dump valve was to allow a means for the nodules to get out of the riser or be discharged from the riser if the pump system or the air injection lift system failed. Similarly, we had a vacuum relief valve down there so that if the collector became clogged or the interface hose became clogged, we could get clean water into the bottom of the riser and therefore clean out all of the solids out of the riser so they didn't fall to the bottom and jam it up. We had a 250 meter, approximately, length interface hose between the end of the vertical oriented rigid riser and the horizontal oriented collector on the seafloor. We had 8-inch hose that we used for the hydraulic lift, the pumps, and 6-inch hose for the airlift. Here too, the sections of hose were about 40 feet long, and that 250 meters of hose allowed us the flexibility to mine with excursions of plus and minus 90 meters of bathymetry or water depth without having to change the length of the riser. And we used off-the-shelf unibolt connectors like the one showed in the bottom photograph to join the links together. I show this slide for no other reason than to remind people that when we sit at our desk in an office, comfortable and warm, we tend to think about pictures like the one on the left. That's a work basket under the rig floor. That's where we had to attach all of the various power and communication cables to the riser as we were deploying pipe. But the picture on the right is another photograph of that exact same work basket. So it's just a reminder that things aren't always as calm as we like to think they are. So, collectors. Our primary collector for the OMI PMT was what we call the 2-meter or the 2M hydraulic collector. This was an incredibly simple, passively towed 2-runner sled device. We had basically one moving part on that machine. We had a 20 horsepower submersible electric motor. We literally put an outboard motor propeller on the output shaft of that motor. We put a duct around the outside of it. We put a fairing on the front end and the shaft end of the motor, and that was our power, period. The 2-meter collector had an active width of 2 meters. That's where we got the name. It consisted of 4 independent dredge heads, which you can see here in this lower picture. And the dredge heads were allowed to float a little bit relative one to the other. And the bottom, the lower limit of that movement was fixed by a cam, basically, that went across the length of the vehicle. Another important consideration for our collectors is we tried very, very hard to make sure that the bearing load of the collector on the seafloor was less than 1/2 a PSI. We also used again, very simple passive device. It was a fin or a cloth sail in the case of the of the 2-meter collector here. And it was used for hydrodynamic stability during the deployment and recovery operations during towing. And it was most critical when we were landing on the seafloor, because it meant that the runners, the bottom of the runners would be facing forward, and we would always land right side up. The 3-meter collector was essentially identical to the 2-meter collector. It's just that its active width was 3 meters, and therefore we had 6 of the floating dredge heads as opposed to 4. But otherwise, it was essentially the same design. One significant difference: the 2-meter pump was just an electric motor with a propeller on it. The 3-meter pump was a commercially available axial flow pump that was a little bit more efficient. We actually used the same 20 horsepower motor to drive it, but we drove it at more like 25 or 30 horsepower. So this is a concept sketch showing a couple of dredge heads. Again, I can't emphasize enough how simple the functionality of this collector or these collectors was. The moving water, it's the only thing that we used to do all the work, was the water that came from that pump. So that moving water was used to separate the nodules from the seafloor, to eliminate the sediment that was removed with the nodules. It was used to transport the nodules within the collector, both vertically and then transversely. And it was used to introduce the nodules into our riser system. Reliability is key. And in our opinion at the time, and mine today, is that simplicity equals reliability. We followed the 1960s U.S. Navy KISS principle, which stood for Keep It Simple. And again, I'm still a strong believer in that, and I emphasize how simple our design was with that one moving part. And also I'll mention that that moving part, that propeller, did not come in contact with the seafloor or the nodules or the majority of the sediment. So the wear and abrasion associated with this simple design was actually quite minimal. Again, this is a detail showing the flow of the dredge head. Water from the propeller pump came into a header, and that was used to form jet sheet nozzles. The Coanda effect caused the flow out of the nozzles to follow the shape of the dredge head. The water scoured and lifted and entrained the nodules and sent them up the ramp. And we actually got entrained water, so we had more flow coming out of the discharge of our ducts than what we put in at the bottom through the nozzles. The nodules were transported up the inclined ramp or duct portion of the dredge heads. The flow was very turbulent, and therefore the sediment was washed off the nodules, and then it was discharged out the top, and I'll show you that here in a second. And the nodules were also raised up within the collector, which then allowed us to transport them horizontally. Yep. So I'm going to move quickly. We rejected oversized nodules in 2 places, one at the bottom of the dredge heads, one at the discharge of the dredge heads. Across the back of the machine, we had a hopper that we used to eliminate the sediment and transport the nodules into the center. We had 3/8 openings. That was enough to let the sediment, dirty water if you will, pass through, but redirect the nodules down into the hopper. There were jet sheets in the bottom, or jet sheet nozzles in the bottom of the hopper, and that's how we transported the nodules into the center of the machine. There were some gravity actuated dump doors that would allow us to get rid of a clogged hopper should that exist. This shows the flow pattern in the 2-meter design. You can see the, whoops, back up here. You can see the flow from the simple motor split going to the 4 dredge heads, additional water supplied to a header at the back of the hopper. And there was a couple of simple adductors thrown in there just to try to increase the flow. Again, 3-meter collector, the same, the difference being that we had a little bit more sophisticated, higher efficiency and higher horsepower pump to drive the machine. Hydraulic collectors work. They have a proven track record. There's 600 tons of nodules delivered to the deck of the ship. I want to just mention bow waves quickly, because bow waves can have a very significant impact on the efficiency of a collector. The sketch on the left-hand half of the left figure there shows a collector with maybe an optimum bow wave, very small bow wave. The right-hand half of that figure shows a large bow wave, and the photograph on the right shows an actual windrow that was formed by a bow wave. The bad news is that these bow waves act as plows and drive the nodules off to the side of the collector, and therefore make the collection much more inefficient. So as I wind down here, I want everybody to remember that KISS principle. Keep it simple. OMI hydraulic collectors embody the KISS principle. We use seawater to perform all of the collector tasks. They required minimum horsepower, basically 10 horsepower per meter of active width. It was a simple, reliable design with only one moving part. That part was not in contact with the solid materials. And we had a very simple approach to making sure we always landed right side up on the bottom. We had very, very good collection efficiency as long as there were not bow waves. We did not have good collection efficiency when there were bow waves. We got sediment rejection down at the seafloor as opposed to bringing it up to the surface. We had something on the order of about 1% or a little bit less than 1% of sediment that made its way all the way up to the ship. Collector bearing load on the seafloor, again, about a half a PSI or less. And we rejected the oversized materials in a passive way. Now that's not to say there aren't lots of opportunities for improvement. We had issues, we had failures, we had problems. Clearly more reliable submersible pumps would have allowed us to put a lot more or a much larger quantity of nodules on the surface. We could have used redundant critical components like that motor. One big issue would be to improve the active width of the collector so that it equals the total width of the collector, right away increasing our collection efficiency. I think more needs to be done to eliminate or minimize bow waves. I think more can be done to reduce the bearing load even farther, thus reducing penetration, thus reducing bow waves. Sediment rejection, again, we had less than 1% at the surface. I think we could do better. You might consider a steerable collector if your CONOPS for your mining operation does say that you want to mow the lawn and have side-by-side parallel tracks. There's probably a way to do that without necessarily driving the collector with screws or treads. And just a comment on the state of the art, the computers, the sensors, the things that we used in the 70s are archaic compared to what's available today. So there's room for significant improvement there. Conclusions, pretty straightforward. We were very successful in what we did. We believed and followed that KISS principle. Again, OMI favored hydraulic designs. We proved the technical feasibility. Mention again the fact that we considered nodules only a surface deposit and ignored anything below the surface. We found out the hard way that collector reliability is key. It's a long way away, and I would suggest that you need to be prepared to lose equipment. I didn't mention it in my talk, but in 1972, Inco lost a collector and a 25,000-foot long cable in a collector test due to a winch failure. In 1976, we lost another collector and its cable, or a portion of the cable, because of a collector failure, a cable failure. And in 1978, in the third PMT cruise, we lost a mechanical collector and a bunch of hose, and again a bunch of cable because of a hose failure. So there is a saying, don't put it in the water unless you can afford to lose it. Be prepared. Have a contingency plan. So thank you. I had originally intended to show a bunch of slides of different collectors, and I'll thank Interocean Metals and Comra for providing me with these two.
Thank you very much, Ted. That was a terrific presentation. I think of the most exhaustive test that I've seen of collectors in my short career. Let's turn to all the participants and questions. We have maybe 5 to 10 minutes for some questions. So shall we begin on my left, and we'll just sweep around the room.
One small question. How did you measure the collection efficiency, and how much is it?
How did we measure the
Collection efficiency.
That's a good question. Most of the true collection efficiency that we measured was done in the test pit, right, on land. The work that was done during the deep sea tests and the subsequent pilot mining test, that was more qualitative analysis based on what we thought the distribution would be. And I didn't really mention it, but in that slide that showed the very modeled appearance of nodule distribution, the density of the nodules on the seafloor can go on for many, many kilometers, being very, very dense. And it can drop to 0 in just a few tens of meters. And that gray, white, dark modeled appearance really, truly is representative of what that distribution was in that particular site. So it changes a lot.
So can I extend this question? What would be your impression? Is the collection efficiency is higher in the areas where nodule density is lower, or it's higher when the nodule density is higher?
That's a good question, and I'm not sure I have a real answer for you. The biggest impact that we saw on collection efficiency was the bow waves. And it was often difficult. I mean, in the mining environment, even though we had cameras down there in the front of the machine, the mining hose dragging on the sea floor and the activity of the machine itself often meant that we couldn't see any nodules in front of us. So everything was based on the measurement system, the nodule counter and the hydrophones. And believe it or not, a hydrophone on a collector is an excellent way to determine throughput, because as the nodules go through the machine, they make a lot of noise. And you can just tell from, with your ears whether or not you're doing well. But the bow waves, they affected efficiency more than anything else.
Thank you, Ted. Maybe a couple more questions. We'll go around the room. Yes.
Thank you, Mr. Ted Brockett. The year 1978 was very, very important for me also, because I entered at that year university. You are one of few people experienced such a large-scale pilot mining test in Rio City. Thank you very much. And the result of the OMI pilot mining test gave me a lot of lessons and inspirations as well. The reliability you emphasized for commercial mining is quite important, I agree. However, the simplicity itself does not give the final solution, I believe. Your design principle, KISS, the final S was stupid. I have changed the final S from stupid to smart in order to get the capability, the aerial coverage of the collector, so that we, during the last 20 years, in the middle of the last 20 years, we have changed the design concept from simple and stupid to simple and smart, to get more nodules from the seafloor. In this sense, the steerability of the collector machine is indispensable factor to get much more area to harvest the nodules from the seafloor. And at the same time, the OMI plan did not include the concept of buffer intermediate storage tank station. How do you think about flow assurance of the slurry flow? Did you have any serious problems in the pilot mining test in 1978? Direct introduction of the nodules to the lifting pipe didn't raise any kinds of technical problems?
I guess the easy answer for me to that question is no. There weren't any problems. I will say at one point on the second pilot mining test cruise, I was not participating in. I did not participate in. They were testing an airlift system, and they did have a problem with it. And the nodules that were in the riser fell back down, of course, when the lift system stopped. The nodules did not all exit out as we had hoped. And some of those nodules, and I guess some did exit, but some also went down the flexible hose and jammed inside the hose. So once they recovered the system, it was a lot of work to get those nodules out. And when we did this work, it took a full 48 hours to get the collector from the deck of the ship to the seafloor. And it took 24 to get it back, right? So this idea of reliability is critical because on a mining ship that may cost $250,000 a day, I'm not sure what the current price is, you don't want to be completely shut down for a minimum of 3 days just because you had a part fail on a collector. Right? And that 3 days is only if you have a standby collector. And I've got to say, I like your definition of KISS much better than the Navy's definition.
Thank you.
But you know,
we probably have time for just one more question. Yes, please.
I'll see if this works. From a reserve estimation point of view, do you have an idea of the size of the SMU?
I'll be honest and say I don't. I think if we're talking about a commercial scale, collection device, my feeling is that you can design a collector, for example, one of these hydraulic designs, and you can size it as an example for a pilot mining test, right? And assuming you go out and you're successful, that same collector device can be expanded, right? So now instead of having one collector, basically we have two, but we gang them together behind a tow frame or an attachment point. And that 2 or 3 gang machine might be 20 meters wide, as an example, right? And maybe that's good enough for your first production system or maybe your pre-production system, whatever you want to call it. But that same system can be expanded again simply by ganging multiple units together. And I don't really know what the upper limit is, but I don't see it impossible at maybe even 40 or 50 meters at some point. It becomes more an issue of handling and how you're going to get this equipment tied together. It's not likely you'd be able to launch and recover it all as a single component. You'd probably have to do some assembly work with the pieces, in the water column somewhere.
And track length?
Sorry?
How long would you run it for?
Oh, you mean distance?
As long as you want.
Oh, I don't know. I mean, I wasn't on the exploration side of things, and I don't remember the size of the mine sites that we were working on, but they were definitely tens of kilometers long. I don't think they were hundreds. I just don't remember.
Okay. And another question, I suppose, is talk about reject of oversize. Do you have an idea of the percentage of reject? from an ore loss perspective?
No, I don't, but one of the things I don't think I talked much about is that 9 5/8 OD pipe that we used. We had decided that we really didn't want nodules into our system that were larger than about 2 inches in diameter, because we thought 3 of them could all be lined up just perfectly and jam up the riser. So during the PMT, we took pains to eliminate anything that was bigger than actually 2 3/16, but call it 2 inches. A commercial scale riser is going to be larger. And I don't know if you noticed the one picture that was on there of the 3 gentlemen standing around a nodule that was literally that big. There are anomalies or whatever you call big nodules or nodule-like things down there on the seafloor. And I've got a number of nodules in my office and at home that are maybe that size, right? So there are nodules down there that are a lot bigger than what we were focused on. But I do know that in our area, or what was our area back in the 70s, the OMI claim sites, the nodules were generally in that 2-inch range and smaller. There weren't a lot of the very big ones.
Thank you.
Thank you, Ted. I think this is a great conversation, so we'll entertain one more question.
Ted, I have one question regarding what you just said, expanding the system on seabed. What do you do on sea level? What do you do with the nodules when they go?
Well, that's a good question, and one, I'll say it's outside my area of expertise, but we were looking at some storage on the mining ship itself, right? And then I'm going to say transfer of the nodules to the transport vessel through hoses. And I don't remember the details, but in kind of a general sense, there were holds on the mining ship where the nodules would be temporarily stored in the event that there was bad weather and you couldn't make the connection with the transport ship. There was the ability to have at least a few days of storage on the ship, and then that could be refluidized or converted to a slurry and pumped over to the other ship.
The point I wanted to make is you said I don't know what the maximum capacity is. That might be the defining factor for your maximum.
Yeah, I think so, and so is going to be the size of the riser pipe and its ability to transport the nodules from the seafloor up to the surface.
Thank you very much, Ted. I think you may have come the greatest distance coming from Seattle to here, and it took you 2 days, and we are very appreciative of your expertise and clearly the knowledge that you brought to the conversation. So thank you very much.
Thank you.
Thank you very much to the speakers. That's a wonderful experience they have shared with us. Now we're going to move to the second theme, is emerging international standards for mineral resource evaluation. And as chair, we have Matthew Nimo and Pedro Madureira.
The first talk will be on information needs of financiers, investors and resource managers from Michael Stanley, mining specialist, World Bank. So we're all pretty interested to hear what a financier might have to say about all this, particularly myself. So could you come up and please?
Thank you very much. I'm losing my voice, so this may be a short, quick, sharp presentation. As I said in my introductory comments this morning, I'm a mining engineer and an economist, and I cover a geography that starts with Afghanistan and ends with the PNG and the Solomon Islands. And so it's a very large, expansive territory. And the World Bank Group advises governments on resource development. And within that line, we are increasingly looking at governments ensuring that they are getting a good and comprehensive mining development contract. If I control this too. Bottom one. There we go. Okay. I have 2 key messages today. One is that we have seen a profound shift in the mining industry, probably starting about 1995, 1998, in what constitutes sustainable mining. And in my presentation, I will show you that we've also seen a very profound shift in the locations in which sustainable mining is taking place today in 2014.
The second big point that I want to make is that financiers, investors, and resource managers really are challenged now to go beyond strict regulatory contractual compliance. Strict regulatory and contractual compliance is not enough to constitute attracting the financial resources that one needs from financiers and investors, including World Bank Group, to undertake a major mining operation. And that you will see in my presentation that we're looking at integrated landscape management, emphasis on environmental social performance. And within this presentation, I meant to point out at the beginning, we're focusing very much on terrestrial mining here. So this is a presentation on mining that has been taking place for the past 30, 40 years. So the global trends, what is going on in 2014 in the global mining industry? Since the year 2000, we've seen a lot of cyclicity in commodity prices, a lot of volatility. Certainly, I think everyone knows the story of the commodity super cycle. Arguably, it ended in 2012, 2013, but indeed some metal prices have started to strengthen again. The market response to all of that, of course, was increased exploration and production. And I think that the bottom line on this is that even with improved production efficiency, which I think the industry is achieving, resource extraction use and global population growth and development is actually depleting the existing resource inventories at an accelerating rate. So what we have is much of the developing world starting to go to resource intensity equal to the United States had probably by 1940, 1950, and that is depleting the existing resource stock. And this is just one of several different graphs along the bottom showing you the exploration expenditures and major discoveries in the Western world. There's a global that pretty much shows the same picture, and that is that we're eating into the stock of mineral resources that were built up from the start of the 1900s through to about 1985. Limiting factors that constrain investors today, I think first and foremost is access. I'm sorry, this is in your way. First and foremost is access to capital. Global capital markets are today very thin, and the competition for capital for the mining sector is probably at least 1 to 2 times as intense as it was in the year 2000. There's not enough capital market to sustain all new mining operations on terrestrial opportunities. The second big factor limiting is continued access to mineral resource lands. So if you take a look, if you plotted a map of the world and you looked at mineral resource lands that were prospective and available to investors in 1975, 1980, you'll see that the map is slowly getting smaller and smaller. A lot of resource lands are being taken off the shelf for other competing land uses. The third has to be environmental and social factors. I will underscore in this presentation a political economy reality that the social license to operate has to be in each and every mining venture going forward. And then I think the fourth has always been geologic factors. This is an estimate that came out by a McKinsey group last year, and they said that by the year 2030, probably 11 to 17 trillion of new investment is needed in mineral oil and gas projects in lower income countries. 11 to 17 trillion, this is 2014, between now and 2030. I can tell you that there probably isn't even a tenth of that available in global markets today. And so what you're going to have is a continued contraction of the global mining sector and the inability to raise capital for some of these new operations. And I say that because in 2012, we looked at the average capital investment in a new mining operation, a bulk commodity. It was averaging around $3 billion. It's actually up around $4.5 billion now, of which 60% of that investment is in infrastructure. And if you follow the iron ore story in Guinea and some other very large, Mongolia and some other large operations, we have proposed mining investments now up to about $12 billion for bulk commodities. So there's not enough capital in the capital markets to supply all of these proposed operations, and the contraction is probably continuing going forward. The International Monetary Fund and World Bank Group we track where is resource production taking place. And if you look at this map, this is a map, I believe it's probably 2014. We have different metrics to try and understand how resource-rich and resource-dependent a country is. And we use metrics such as 25% of gross domestic product or 20% of export earnings. And what you begin to see is that the resource industries have moved from the developed nations, the OECD nations, into the developing nations. And in 2005, we had about 42 countries that were either resource rich or resource dependent. By 2012, we were over 50 countries, and by 2018, we'll probably be close to 60 countries. 60 developing nations that previously, if you go back to 1975, did not have major resource production will be defined as either resource rich or resource dependent. And with that, we get a second trend, and that is a very diverse stakeholder group, where we have the governments, we have developers, we have investors, and now we have society. We have community and civil society are part of the political economy, the decision-making process for where mines will go forward. And with that society dimension, then we pick up benefit sharing, and I think that that was in Caitlin's presentation this morning, a discussion of, is there a benefit sharing mechanism for these mining operations to make sure that we have poverty reduction, shared prosperity? And that benefit sharing package that is being negotiated now for large mines largely predicates where the capital is flowing. So the financial community want to know that you have full regulatory, environmental, social compliance, and that you have an equitable benefit sharing package so that we know that we don't have community opposition or local regional opposition to the mining operation. Key challenge to investors, financiers, and resource managers has got to be governance. Governance now is the largest single variable that we look at in these operations. And that is what will define a sustainable mining operation going forward. So as I said before, the number of resource-rich, resource-dependent countries has increased by about 40% since 1995, and most newcomers have a low average income, weak regulatory regimes, and very weak monitoring and reporting capacity. And this is, again, from McKinsey. This just shows you that the resource-rich, resource-driven countries that started between 1995 and 2011, 54% now constitute the low-income countries. And so we have a regulatory environment that has shifted from very well-regulated with high capacity for monitoring and reporting down to weaker governance systems and less capacity for regulatory monitoring and reporting. And often when we give this presentation and we speak of governance, people then ask me, what is the technical definition of governance? And I won't read it today, but it really is about accountability, capability of the government, and inclusiveness, making sure that the government and company have some sort of prior informed consultation with the local communities, and that benefit sharing mechanism is well understood and is enforceable. What do future resource-rich nations look like? I have a whole series of slides, and so I pulled one for deep sea mining, and it's the same story as it would be for terrestrial mining. We've got developing countries, they have low gross domestic product. HDI is a human development indice, and it's a key metric in the financial community to understand the landscape into which you're putting your money. So we look for HDI above a certain ratio point, and 7% of the world's lowest GDPs, 6 of them are Pacific Island countries. Most of these places have a narrow resource base. They have tremendous GDP dependency on fishing, tourism, and remittances, which are the diaspora that go overseas. These nations are characterized by small populations. They have vulnerability to climate change disasters. I mean, you can read this list. It's the same list as if we were doing terrestrial mining for Africa or South Asia or anywhere else. So we have an industry that is moving into frontier places. It is up to $5 billion of investment, and the financial community want to be absolutely sure that these operations have the social license to operate. We used to run in whoops, that didn't work. How can I go backwards now? Yeah. We used to run in the World Bank Group an annual survey of investors, and we asked them, what do you need? What do you look for when you, the investor, are looking to make an investment decision? And unfortunately, this is getting quite dated. I think this is probably 2004, the last time we updated it. But companies would always give the same response. The very first thing they look for is geological potential. Is there a resource there of quantity, quality, that we can make a commercial operation? And then beyond that, they wanted to look at the profitability in terms of the fiscal regime, foreign exchange control mechanisms. They wished to understand security of tenure, so if they had an exploration right or permit, could they go to exploitation, subject to regulatory compliance and review. They wanted consistency of policy and to make sure there was clarity of roles and responsibilities at different levels of government. And they wanted to know that there was a social license to operate, which meant that there was some sort of inclusive process for communities going forward. And stability of legislation, because an investment today, as we all know, cash flows are usually amortized over 20, 25 years, and so you had to have both fiscal stability and environmental and social stability, very predictable and very well defined from the beginning. And then for terrestrial mining, we had this additional point, availability of infrastructure. What's interesting is that beyond the geological potential, everything else is actually in control of the government. And so we have an industry that is moving into governments that are challenged to have strong governance systems. They're challenged to have strong regulatory monitoring and reporting. And yet they actually control where most of the money is going to flow. And this is a summary of the same thing. This is actually by a more recent, this is 2009. I think this is Barry Dolbear, who do an annual industry survey. And they came up with the very same list. The very top of their list is social license to operate. Does that mining operation have full endorsement of all of the stakeholders? And I asked you, Caitlin, this morning. The stakeholders are the government, the investors, the communities, NGOs worldwide. Was there certainty of title, certainty of development approvals, confidence in the environmental social context, the tax and royalty scheme, and an acceptable level of sovereign risk? So this is actually a list that the industry have continued to put out. And I think this morning, Caitlin, you had Agricola as one of your quotes, and I also have that. In the year 1556, Agricola said one of the first and most important things on a mining operation is to reach out to the neighbors and make sure that everyone understands very clearly what is going to happen in that going forward. This is a diagram that we've created excuse me, to show the difference between regulatory regulatory compliance, which everyone has to have in their mining operation, and sustainable development. And so if you go back to 1998 and before 1998, it was really about meeting the ESIA standards, making sure that you had a strong competitive licensing process, that the taxes and royalties and other non-tax revenues that were due to the government being collected. And so that was the regime of full regulatory compliance for the extractive industries. In sustainable development today, and again, as I said, this is terrestrial mining, but look what you have to have now. Local, regional economic development, partnerships for development, infrastructure and transport corridors, shared infrastructure. If the mining company is building a power plant or an onshore metallurgical processing facility, that somehow there's a positive externality to that. Community development agreements and social and human development. The financial community will look at those HDIs that I mentioned before, human development indices, and make sure that they're starting to go up as the mining operation is going up. And so sector sustainability is really based on a very strong system now of strict regulatory compliance and then a series of performance-based metrics over here. I'll come to this again later, but increasingly we look at what we call integrated spatial planning. What is the context of that mining operation in the larger landscape on which it is operating? Is it complementary to other land uses or other sources of income, fishing? Is it complementary to other activities the government is undertaking in terms of its development objectives? And can we show that the mining industry in that country is actually enhancing and leading to those improved HDIs, Human Development Index measurements? This is probably the most detailed graph I will show you today, or graphic element. In the World Bank, we have created a system of checks and balances, a whole series of technical considerations we look at when we're looking at a mining operation. We start with the award of contracts and licenses. How did that person get that concession? Was it transparent? Was it competitively assigned? Is there the capacity for regulatory monitoring and reporting of operations, socially, environmentally, and fiscally? Is the government adequately collecting the taxes and royalties it's due? Are they managing those revenues well? because it's pointless to have a very robust mining country and the government is consuming all of the money in that generation or consuming it in non-recurrent ways, going into places that's not really helping build the economy. And then lastly, do we have environmentally and social sustainability projects? So that's the broad schema for governance as we define it in 2014. And these are some of the details down here. I can tell you that if we looked at this in the context of deep sea mining, it would be a very complex space, even inside the World Bank Group. We're the largest federal development bank in the world. And we have gone through this conversation, and we have so many different players within our own organization that would be necessary to ensure that we had a very holistic and comprehensive measure of the sustainability of the mining operation. So you can imagine if you have a developing nation with weak governance, weak regulatory oversight, the challenge that they're faced with to understand whether all of this is leading towards sustainable development. There are a series of global safeguard policies for mining today. They're environmental, social, and fiscal. And they apply in all mining operations that take place where you've pulled money out of commercial markets. This slide was created for a different purpose, and so there's a whole series of uncertainties here. The only one that I've underlined for you today is that we look at clarity of roles and responsibilities. We look at the effectiveness of policies, but we also want to make sure we have verifiable mineral resource information from the beginning. And this came up this morning. What is the source of that information, the competent person someone raised, right? And can we take a very confident position that that mineral resource that is being reported is indeed what will play out through the mining operation itself? But there are a series of safeguards that also come into play, and that's, you probably can't read it, but these occur down here. And so there are a series of policies on environmental performance, social performance, the Equator Principles, voluntary principles, the International Council for Mining Metals. They all have a series of safeguards that get applied through the financial community onto the mining operation. And this makes it especially difficult in developing nations where we have weak governance, weak regulatory oversight. And now, in addition to full contractual compliance, these other policies are put in by the financial community right there. And this is a summary of largely what I have said already, that there are so many challenges now within these developing countries. And there's one that I think we probably should discuss in the questions, and that is that we have a large NGO community that are now also stakeholders. So in a mining development decision in 2014, the investor, the government, the local communities, and increasingly we have NGOs that could be based in London, Paris, New York, Sydney, you name it, where they actually will exert a tremendous influence on the application and monitoring and reporting of those safeguard issues that I pointed to you before. Key challenges going forward: financiers, investors, and resource managers require resource assessment information that supports sustainable development. And let me give you, I think, the most comprehensive example I can think of. It's from India. So here we are in India. India has unquestionably, in South Asia and East Asia, one of the strongest global science and engineering expertises available. India has state-of-the-art management systems. And India has guiding policies for the regulatory agencies, and India has a very robust civil society. India has everything that you would want to look for in a mining country, terrestrial mining. India today is significantly challenged to provide resource information to ensure good governance. And in actual fact, the Shah Commission of 2013 found that many of the mining operations in India are not in compliance, and they have taken judicial actions to stop the mining industry in India. The World Bank came in and we looked at Odisha State, and we began to undertake an analysis of what could be done to bring mining back into sustainability in the Indian context. And so we defined a pilot area in the state of Odisha. It's right here. It's called Kyanjar District. It's a big iron ore producer. And we began to ask ourselves, what do we need to see there to make this sustainable? And we focused on the resource classification problem. very quickly. Let me go to the next slide. Does that look familiar to everyone? Yeah. We discovered that India has the 1997 UNFC, and that it was not adequately capturing the social and environmental performance metrics that the government is looking for, the NGOs are looking for, and frankly, the financial community is looking for. India is no longer attracting international capital to its mining sector, its terrestrial mining sector. And so we have been working with ECE and others, with the Indian Bureau of Mines and the Ministry of Mines, to do a pilot of the UNFC 2009 resource classification system. Because I think everyone that has gone through this pilot appreciates it was not enough to have geological knowledge and project feasibility. We needed this third axis right here. And I won't talk about this too much because I know you're going to present this tomorrow. Is that right? Tomorrow, okay. We needed this third axis. We needed to be able to do mine planning and mine development in India that told us everything that I had in those previous slides. Right? And it had to be embedded in the resource classification system, so that the Indian government would know and the state of Odisha would know if I have two iron ore resources and they have exactly the same quantity and quality, but they have different landscapes on which they sit, and they have to be integrated into that landscape, that the Indian government will know which of those two is more likely to be a sustainable mining operation going forward. So we are partway through this application, and I can tell you it's been very difficult. It's been very challenging. I'm looking over at Charlotte and David. We've been working collaboratively on this with the Bureau of Mines and with the Department of Steel and Mines in Odisha. But this is the direction in which we are trying to go. And I will show you one more slide right here. There's a lot of detail here, but it's just to tell you that that SDF that I showed you on the last page is actually, where is it now? I can't even find it here. The UNFC, there it is, UNFC, risk mapping. So we've tried to improve the data collection with statistical data and spatial data. We've applied now a framework, and I think this is one of the key messages, that a resource classification system has to sit underneath a broader sustainable development framework. You have to have some sort of overarching metric for sustainability, and then to ask yourself what resource classification system is appropriate, and bring it in underneath. And this is a discussion that we're going to take place this week. We've gone through improved data collection, improved resource assessment, as was asked this morning. We have run it through the Sustainable Development Framework, and now we're applying that UNFC that you saw on the previous page. We're applying this right here to inform the government on which of these resources truly is a candidate for mining going forward. And therefore, that will signal to the financial community, who have now since departed, that those resources are actually viable, and to invest in those resources going forward. So some key messages. Let me summarize this. Governance and investment risk are intertwined. If you have a country, or you have a state, or you have a small local area with weak governance, you have very high investment risk. You can't unbundle those two. We call it this, those are two sides of the same coin: governance and investment risk. Financiers, investors, and resource managers now are going beyond strict regulatory compliance. That was the thing of the 1990s, and they've moved into sustainable development frameworks based on integrated landscape management. What is the context of that mineral resource in terms of other activities that could take place on that landscape or onshore where you're doing metallurgical processing? And clearly there now is a much greater emphasis on environmental and social performance. And as I said, the stakeholders in that will be the local government, the investors, the financiers, and probably NGOs that you have not encountered because they live in another part of the world. There is a political economy to this that I think we really can never underestimate. The challenge going forward is to get a resource classification system aligned with the Sustainable Development Framework. So if you're having a conversation this week on what is the appropriate resource classification system, it really begins with what is our SDF, our Sustainable Development Framework. And then I think with that, it would inform the conversation around the socioeconomic impacts and that third axis on the UNFC classification system. And as a bit of a caveat, we haven't finished our pilot yet, so I'm not necessarily saying that is the resource classification system. But that's the one after going through this exercise exhaustively for a year that we've come upon, that we think probably is appropriate. It has, in many ways, the right typology with those 3 axes to fit very well under India's sustainable development framework going forward. That's all of my work. Thank you.